And here we are, ready to finish up the definitions of acids and bases. The final definition, the newest definition, the broadest definition, is the Lewis definition of acids and bases. Okay, you might remember Lewis from the Lewis structure, the Lewis diagram. This guy was prolific in his thinking about chemistry. The Lewis definition of acids and bases is kind of a radical departure from the Bronsted-Lowry and Arrhenius definitions, because it changes the focus entirely. It moves away from protons and instead moves over to electrons. Okay? So an acid, for Lewis, accepts a pair of electrons. Notice that reverses it. Arrhenius and BL said that an acid was a proton donor. For Lewis, it is an electron pair acceptor. And a base is the electron pair donor. Okay. So if Bronsted-Lowry covers 99%, then Lewis brings the coverage up to 100%. It covers all possible acids and bases. And it covers a few things that Bronsted-Lowry didn't. But now, let's go ahead and look at the reaction of ammonia. I'm going to go ahead and draw it out this time. With hydrochloric acid. According to the Lewis acid definition, or the Lewis definition of acids and bases, this is what's happening. This pair of electrons is attacking the proton. Because, chlorine is very electronegative, much more electronegative than hydrogen, so you have positive or partial positive and partial negative charges on your hydrogen and chlorine. So this partial positive is sort of attractive to the very, very negative charge of the electrons over on ammonia. So the electron pair attacks the hydrogen, or to put it another way, the ammonia donates the electron pair. The hydrogen over here accepts the electron pair. This bond is broken, sending those electrons over to the chlorine. So when everything is said and done, you have ammonium with 4 hydrogens bound to it. It has a positive charge. And you have chlorine with 4 lone pairs and a negative charge. One of the strengths of the Lewis acid definition is that it puts the focus back where it belongs. All other chemical reactions are about the movement of electrons, not the movement of protons. Electrons are small and fast, protons are big and slow. Chemical reactions are always about the formation of chemical bonds, and chemical bonds are where electrons live. And chemistry is about electrons. So Lewis is much more in keeping with the rest of chemistry. Another advantage to Lewis is that Lewis explains something that not even Bronsted-Lowry can explain, namely the acidity of boron trifluoride. Okay? It acts like an acid, but it has no protons to donate. You throw it into solution, it will not, make H+, it will not make the hydronium ion H3O+. Neither of those can do that. And yet, any reaction you care to name, boron trifluoride acts like an acid. It will react with any Bronsted-Lowry or Arrhenius base perfectly fine. How does that happen? Well, Lewis explains it just fine. You will recall the bonus question on that practice test I gave out had ammonia reacting with boron trifluoride. And this is how. It's because boron has that big old empty p orbital just waiting to accept a pair of electrons from ammonia. So ammonia is an electron pair donor. That makes it a Lewis base. And boron or boron trifluoride, I should say, is an electron pair acceptor, and that makes it a Lewis acid. Lewis acid is the broadest, the best definition, because it will explain every acid and base you come into contact with, and it will explain it in terms of electrons, which is a really great and awesome way to do it. But it is not as emotionally satisfying as the other two definitions. Those just are really simple, really easy to remember, because all you got to do is look for the proton, right? Find the proton, you found the acid. So most of the time when we talk about acids and bases, we're going to be using the Bronsted-Lowry or Arrhenius definitions. But the Lewis acid is technically the best, and technically correct is the best kind of correct. So you definitely should know Lewis acids and bases. Another reason to remember Lewis acids and bases is because if you continue to study chemistry, they're very applicable to organic chemistry. They're great for organic chemistry. In organic chemistry, they often talk about nucleophiles and electrophiles. Ooh, wow, that's awful. Okay, electrophiles. A nucleophile is something that is rich in electrons, and an electrophile is something that is electron poor. Okay? In other words, negative charge or negative partial charge versus positive partial charge or positive charge. Okay? You look at, say, ethanol, CH2OH, you have carbon bound to carbon, and they are bound to other things, specifically mostly hydrogens, but also an OH group. This OH group, oxygen is very electronegative, has a significant negative partial charge. It also has two pairs of electrons. It's electron rich, so it's described as a nucleophile. Whereas this guy over here, the carbon bound to the oxygen, you could describe it as being electron poor because it has a lower electronegativity. So it would be an electrophile. And there are different reactions that will interact with electrophilic regions versus nucleophilic regions and things like that. And you can see that this works perfectly well with the Lewis definition of acid and base. If you're electron poor, that means you want to accept an electron pair, so that would mean that you would expect this hydroxide on ethanol to be very slightly acidic. At the very least, it's going to be somewhat acidic. And it is. It is a very, 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 very weak acid. And you would expect the carbon bound to the oxygen to be very weakly basic. And in a way, it is. When I say very, very, I mean very, very, very weakly basic. Electrophiles and nucleophiles are another way of talking about Lewis acids and Lewis bases. If you continue to study chemistry, that might help you think about the ways that some, not all, but some organic compounds will interact with acids and bases. So you've already seen some of these, the way that I abbreviate acids and bases. So I can talk about acids generally rather than a particular acid. I might write HA, HA, which would separate into H plus and A minus. Or HX, that would be a halo acid, hydrogen chloride, hydrogen fluoride, hydrogen bromide, and so on. Remember, the halogens are abbreviated as X. So those are different ways to write about different acids. And bases are often written BOH, which would break apart into B plus and OH minus. But just to take into account the Bronsted-Lowry definition, I might write just B, which can react to accept a proton to make HB plus and OH minus. Those are different ways to abbreviate acids and bases. Next, we're going to talk about neutralization reactions. But before we get into that, I want very quickly to talk about the fact that you don't actually get free protons flying around in solution. We often talk about them as if they were, but technically they're not flying around in solution independent. Instead, what happens is you throw your acid into water, and that's when it becomes an acid. And that's why we differentiate between hydrogen chloride and hydrochloric acid. Hydrogen chloride is the solid. Hydrochloric acid is what you get when you dissolve hydrogen chloride in water. Because this is what you see I've already mentioned this once and drawn it once. But what you get is what's known as the hydronium ion. That is H plus bound to H2O. Let's go ahead and draw our compounds again, show their Lewis structures. We can explain this in terms of Lewis acid and Lewis base. You have your nice negative electron-rich oxygen. It attacks the hydrogen, breaking that bond, leaving you with hydronium. With one free electron pair or non-bonding pair, and chlorine 1 minus. So you don't actually get, a bucket of protons floating around in solution. You just get the hydronium ion. We often talk about the hydronium ion specifically, and it will come up and be fairly important later. But for now, it's just something to remember. And we often, even though they don't necessarily technically exist, we often do talk about free protons floating around, just because it's simpler, it's slightly faster to write it out that way. So next we have our neutralization reactions. Neutralization is what you get when you mix an acid and a base. They react together and sort of, not entirely, eliminate one another's acidity and basicity. Going back to the oldest definition, the Arrhenius definition, when you mix an acid and a base, the result is a water and a salt. Okay, so here you see hydrochloric acid plus sodium hydroxide reacts to form water and sodium chloride, table salt. But you move it up to the Bronsted-Lowry definition, in which a base is a proton acceptor and not necessarily a hydroxide donor. You could mix, for example, sulfuric acid and ammonia, and that would give you ammonium sulfate. No water, but the acid and base have still neutralized each other. You get a salt, but no water. And then you move it up to the Lewis definition. You mix ammonia and boron trifluoride, and what you get is a coordinate covalent compound. It's not even a salt. However, for the most part, like I said, we'll be talking about Arrhenius acids and bases, and sometimes we'll be talking about Bronsted-Lowry acids and bases. So you can usually expect a salt of some kind to come out of a neutralization reaction. You can also usually expect water. Not always, but sometimes. So that is yet another reaction to add to your growing list of reactions to remember. Combination, decomposition, combustion, double displacement reactions, and now neutralization reactions. Acid plus base will neutralize one another, usually producing water and salt. If not water, then at least usually a salt, and if not that, then something complicated that I probably wouldn't ask you about on a test. Don't take that for granted. Now, let's back away from acids and bases for a little bit and talk about electrolytes. If you've seen the movie Idiocracy, not a great movie. I thought it was a little bit ham-handed, but at least they popularized the term electrolytes, because Brondo's got electrolytes. What is an electrolyte? An electrolyte is a salt. That's really all it is. An electrolyte is something that you dissolve it in water, it conducts electricity. Okay, so first I want to talk about dissociation and ionization versus dissolution. Dissolution means something entering solution. Sodium chloride will undergo dissolution, but so will sugar, C6H12O6. But sodium chloride is an electrolyte, but table sugar is a non-electrolyte. They both dissolve, they both undergo dissolution or solvation. Solvation is another word for that. Okay, solvation. But table salt does undergo, and table sugar does not undergo. Let's make that a little bit clearer by changing color. Table salt does not undergo dissociation or ionization. Dissociation or ionization is what a salt does when it goes into solution, when it breaks apart into its component ions. That is why salts are electrolytes, and that's why sugar is not an electrolyte. Because when you dissolve these ions in solution, they are now free to move around, and that is what electricity is moving charges. It can be moving electrons, or it can be moving ions. Okay? So a solution of water with salt in it, some kind of salt, any kind of salt, will be an electrolytic solution. It will conduct electricity, but a solution of sugar water will not conduct. It is non-conductive because there's no ions. It is not an electrolyte. There's no dissociation. There's no ionization. And that brings us to yet another 15-minute marker. So let's go ahead and call it for today. We will continue our discussion of electrolytes in our next lecture.